So yesterday we were discussing about the lattice vibrations of a one-dimensional diatomic chain, and we discussed that if we have two different atoms in the diatomic chain, then we are going to get dispersion curve like this, in which we have at the lower frequency we have the acoustic branch, and then we have at the higher frequency optical branch, because this the frequency corresponding to this branch lies in the infrared region, or the molecules in this region will respond kind of ionic crystals in this frequency region. They will respond to the infrared radiation. That's why the name optical branch. And the acoustic branch and optical branch, they are separated from each other by a forbidden or not allowed band gap. So you see the lowest frequency in the optical branch occurs at the zone boundary, and it is under root 2k by m. So it depends upon the motion or vibration of the ion with smaller mass. In this case, the ion with higher mass will remain stationary, it will not move. And the opposite thing happens for the acoustic branch, where the maximum frequency is obtained at the zone boundary, and it is equal to under root 2k bar divided by capital M. So in this case, the motion of ions of a smaller size will not be there, only the ions with higher mass will vibrate. So this we discussed yesterday, and before we proceed further, there is a correction I need to tell you. Suddenly I realized that it is a correction. So the day before yesterday, we discussed about the one-dimensional monoatomic chain lattice vibrations, and we calculated some frequency, maximum frequency. So earlier it was written here 2 into 10 to the power 13 hertz. That was a calculation mistake. Yesterday somehow I realized that there is a mistake. So actual frequency is 10 to the power 14 hertz. This frequency lies in the infrared region, not 2 into 10 to the power 3 hertz, because the frequency band for the infrared radiation is from 3 into 10 to the power 11 hertz to 4 into 10 to the power 14 hertz. So if you do this calculation, you will get this frequency 10 to the power 14 hertz. So there was a mistake. I corrected it. I hope you got it. So then we calculated the frequencies corresponding to the optical branch and the acoustic branch, and the frequency for the acoustic branch is given by this relation. And if we are interested to see the frequency versus wave vector relation near the k is equal to 0 position, means at the center of the zone boundary, then we will get the frequency that would be Ka under root 2k bar divided by m, capital M plus m. And near the center of the zone boundary, the phase velocity and group velocity will be the same. And this is the maximum frequency of the acoustic branch, and this is the minimum frequency of optical branch. We calculated all these frequencies yesterday. This is the maximum frequency of the optical branch. So the width of the forbidden gap depends upon the ratio of the two ions, the ratio of the mass of two ions. That is, it is given by, or it depends upon capital M divided by M. The larger is the ratio, the greater is the width of the forbidden gap. If we have the two ions of equal masses, forbidden gap disappears and optical and acoustic branch coincide at the zone boundary. You can also notice one thing, that if you consider the one-dimensional monoatomic chain in which the zone boundary is from minus pi by a to plus pi by a, but in the case of diatomic chain, the zone boundary is from minus pi by 2a to plus pi by 2a. So this means the unit cell is of double size in the case of diatomic chain, whereas the Brillouin zone is half the length of Brillouin zone in case of one-dimensional monoatomic chain. So whenever you reduce the length of the Brillouin zone by half, we will get a forbidden gap at the zone boundary. So we also did this, that for the optical branch, the vibration of the ratio of vibration or amplitude of vibration of two ions, which is given by A divided by B, is equal to minus M upon M. So in the optical branch, near K is equal to 0, the two ions vibrate opposite to each other, because we have minus sign here, and the amplitude of vibration is inversely proportional to the mass of the respective ion. So more is the mass, lesser would be the amplitude of vibration. And this is what is shown here. The two ions are vibrating for the optical branch, where lambda is much greater than B or K is close to 0. The two ions vibrate opposite to each other. But for the acoustic branch, the two ions vibrate in phase, and if the masses are equal, so we will get A upon B is equal to +1. So from this diagram, we can see that the two different ions near K is equal to 0 at the center of the zone boundary, they are vibrating in phase. Diamond and HCP lattices having two atoms per unit cell exhibit optical branches, because diamond has abscissa structure, and it has two atoms in a basis. So if we have the abscissa lattice, on every lattice point we put a basis of two carbon atoms, then we will get the diamond structure, and the position of atoms in the basis is 0 0 0 and quarter quarter quarter. Other examples are sodium chloride, potassium bromide, lithium ferrite, lithium fluoride. All these are examples. NaCl, KBr, and LiF. These are the examples of ionic crystals. They have different type of ions. One is positive, other is negative. But in case of diamond or silicon or germanium, there are same type of atoms. So we will get some difference in the dispersion curve if we compare diamond, germanium, silicon with that of ionic crystals. So the frequency of vibrations of these diatomic molecules lies in the optical region. Ionic crystals are known to absorb the infrared light, and hence the name optical branch. This we have already discussed. Now we have plotted the A by B ratio, the amplitudes ratio of the two ions in the optical and acoustic branch, and we will get this type of curve. If the mass of the heavier atom increases, the optical branch, which is this one, the lower one, it will become flat and becomes parallel to k-axis, while the acoustic branch coincides with the k-axis. So this is all has been shown here. If we represent the light atom by this cross symbol and the heavier atom by this filled circle. So for the acoustic branch near the center of the zone boundary, the two atoms are vibrating in phase. That's why the arrow shows the direction of vibration. So the two atoms are vibrating in phase. However, near k is equal to 0 for optical branch, the two atoms or ions are vibrating opposite to each other. Near the zone boundary for the acoustic branch, the lighter atom will not move. So you can see the cross remains at its position. Only the heavier atoms are moving because the frequency is 2 under root k bar divided by capital M. So the lighter atoms or ions, they do not move, only the heavier ions move. And for optical branch, it is the lighter atoms that vibrate, the heavier atoms will not move. Number of normal modes in the first Brillouin zone would be 2n, since each k value corresponds to two modes, one acoustic and one optical. So therefore, like in one-dimensional case, we have in one-dimensional monoatomic chain, we have n number of normal modes. In case of diatomic lattice vibrations, we will have 2n normal modes because each k value corresponds to two modes, one acoustic and one optical, and there are n number of k values. So, and each k value corresponds to two modes. Therefore, there will be 2n normal modes in the first Brillouin zone of this diatomic lattice vibrations. Now we can expand our knowledge or understanding of one-dimensional monoatomic and diatomic chain or lattice vibrations to the three-dimensional lattice vibrations. But we will not do the rigorous mathematics involved. We will just try to understand qualitatively, not quantitatively. After understanding the vibrations of one-dimensional lattice and one-dimensional lattice with the basis of two atoms, we now extend our discussion to the three-dimensional lattice. And as I told you, we will avoid rigorous mathematics. We will try to understand the things only qualitatively. So for this, we consider monoatomic Breve lattice in which each unit cell has a single atom. But now this Breve lattice is a three-dimensional arrangement. It is a three-dimensional entity. The equation of motion of each atom can be written in a manner similar to for the one-dimensional case. Here also the atoms are coupled together because of their mutual interactions. The normal mode solution is, so for any particular atom, the amplitude of vibration is represented like we were representing by xn or yn. Here in three dimension we are representing the vibrational amplitude, means the displacement from its equilibrium position. It is given by vector un is equal to a vector times e to the power k vector dot r vector minus omega t. Here we have vector notations. It is very important. The k vector here specifies both the wavelength, its magnitude is equal to 2 pi upon lambda, and it also tells the direction of propagation of the elastic wave. A vector is necessary here because propagation takes place in three dimensions. The vector A specifies the amplitude as well as the direction of vibration. One is the direction of propagation and the other one is direction of vibration. The two things are different. So accordingly, we will. So what is the meaning of direction of vibration? It specifies the polarization of the wave, the direction of polarization of wave. So, for example, if A vector is parallel to K vector, it will be a longitudinal wave. Or when A vector is perpendicular to K vector, it will give rise to a transverse wave. So in three-dimensional case, we can have the transverse as well as longitudinal waves, but in real lattice, the wave is neither purely longitudinal nor purely transverse, but a mixture of both. When we substitute this equation, when we substitute this equation in the equation of motion of ions, we obtain three simultaneous equations involving three components of A. Now it is a three-dimensional vector, so it will have three components, AX, AY, and AZ. So we will get three equations in the components of AX, AY, and AZ. And when we write the secular determinant in the coefficient of the components of AX, AY, and AZ, we will get 3 by 3 determinant that we need to make equal to 0, and we write the secular equations for this 3 by 3 matrix, and we will get what we will get. We will get we will get equations which is cubic in omega square. The roots of these equations lead to three different dispersion relations or three dispersion curves as shown. This is the dispersion relation between omega and k for a three-dimensional Breve lattice. You see here there are three branches coming out, and they meet at the origin or at the center of the zone. Only the right part of the Brillouin zone is shown because because the omega versus k diagram is symmetric. So we can show only the right side. All the three branches passes through the origin, as you can see from the graph. All are acoustic waves because this is the acoustic region. Therefore, all the three waves are acoustic, and this is expected from a monoatomic Breve lattice. If we have in three-dimensional situation, the dispersion relations are not necessarily isotropic in K space. Means if we are studying the dispersion relation along any particular direction, for example 1 0 0 or 1 1 1 or 1 1 0, so the dispersion relations are different in three-dimensional case along different directions. So this dispersion curve represents only the profile of dispersion in a certain k direction. If the dispersion relations are plotted or acquired in another direction, a new profile will result, which may look quite different from the previous one. In three-dimensional case, therefore, a complete representation of the dispersion relations require giving the frequencies for points throughout the 3D K space. And it is often accomplished by plotting the frequency contours in this space. So many complicated words are written here. It would be the meaning of these words would be clear to you in a short while when we study the graphs. So in this graph, as you have seen, we have three branches coming out, which meet at the origin. And these three branches, they represent the three directions of polarization. When K lies along particular direction of higher symmetry, like 100 or 110 direction, these, these waves may be classified as longitudinal or pure transverse waves. What I told you earlier, that in a in a crystal the waves are mixture of longitudinal as well as transverse direction. They are neither purely longitudinal nor purely transverse. But whenever we are considering the omega k diagram in any specific direction with higher symmetry, and if you remember, when we discussed the Wigner seed cell of BCC and FCC, I told you about some specific points. These points were gamma point, then X point, M point, T point. Do you remember those points in the Wigner seed cell? Sometimes I show you some points. These points are points of higher symmetry. So if we are acquiring the omega k diagram along these these directions of higher symmetry, then the wave will be either purely longitudinal or purely transverse. And under this, usually the longitudinal branch is higher than the transverse branch because the restoring forces associated with the longitudinal oscillations are greater. So in this case, if we ask what is the longitude, which one is the longitudinal wave and which one is the transverse wave. So we have told that the frequency of the longitudinal wave is higher. Therefore, the uppermost branch, it represents the longitudinal vibrations, and the remaining two, the lower ones, they are the transverse waves. They represent the transverse vibrations. And the nomenclature which are used for the transverse and longitudinal waves in the acoustic band, they are known as TA, transverse acoustic, and longitudinal acoustic. So the upper one is longitudinal acoustic and the lower ones are transverse acoustic. So I hope it is clear to you. When we are obtaining the dispersion relation along a direction with higher symmetry, then we will have wave which is either purely transverse or purely longitudinal. But when we are considering or when we are studying the dispersion relation along a non-symmetric directions or the points which have lower symmetry, waves will neither be purely longitudinal nor will be purely transverse. It will be a mixture of both. But still we may refer to the branches as TA or LA on the basis of their polarization along the direction of higher symmetry. It may also happen that the two transverse branches are having the same energy. So in that case, the two branches will be degenerate and they will coincide. So for example, we see the three-dimensional dispersion curve of what is this material? Aluminium. So aluminium on the right side, we saw the dispersion curve along 100 direction, and on the left side we saw the dispersion curve along 110 direction. Only half of the Bedouin zone is shown because it is symmetric about the origin, So you see, along 100 direction, we have only two branches because here the lower branch, the transverse branch, these are degenerate. They are having the same energy. That's why in place of two, we are only having one curve, but actually there are two. And the higher branch, as I told you, the longitudinal branch has higher frequency and hence higher energy. Therefore, this one is the longitudinal acoustic, and the lower two branches, which are degenerate having the same energy, they are known as transverse acoustic. But if we study the dispersion curves for aluminum along 110 directions, now the two transverse vibrations will have different energy, and that's why we will have three branches here. We will have three branches here. We can see it for germanium also. Along one direction. Now germanium has abscissa structure, so the unit cell consists of two germanium atoms, and the atoms are located at 0, 0, 0 position and quarter, quarter, quarter position. So in this case, these represents the lattice vibrations of a diatomic unit cell. That's why in this case we will get six branches, but you see here there are two degenerate branches, and in the optical branch also we have two degenerate branches. Actually there are six, but in the figure, because we have degeneracy, only four branches are there, but actually they are six. Here we have two and one three, two and one three, total number is six. So in the acoustic branch, lower one is the acoustic branch, you have transverse acoustic and longitudinal acoustic, and in the optic branch we have transverse optic, which are degenerate, and longitudinal optic. They meet at k is equal to 0 for the optical branch. Along 100 also, you see we get different type of omega k diagram, but the optic branch here are meeting at k is equal to 0. If you, however, look the same behavior for an ionic crystal like sodium chloride, the LO and TO branch, they will not meet at the k is equal to 0 for optic branch, but there would be a separation. The separation is because a dipole moment is induced. We have Na ion and we have Cl ion, and a local dipole moment is induced, which will cause the two branch to separate at k is equal to 0. So this is the difference between the diatomic lattice vibrations for a non-ionic crystals and ionic crystal. Now we can see how we decide that here we will have, for a diatomic lattice vibrations we will have 6 branches. For a monoatomic lattice vibrations we will have 3 branches, and we need to ask what is the rule for this. So for a non-Bravais lattice means the unit cell contains more than one atom, and if there are any arbitrary 3 atoms per unit cell, so out of them 3 would be the acoustic branch and 3 would be the optic branch. So for example, if R is equal to 1, if R is equal to 1 means we will have only 3 acoustic branch, because here 3 minus 3 would be equal to 0. So we will have 3 acoustic branch. So this is for one-dimensional monoatomic chain. If R is equal to 2, we will have 3 acoustic branch and 3 into 2, 6 minus 3, 3 optical branch. That's why we will have here 6 branch for diatomic chain. And similarly, we can study for other type of Breve lattice. So germanium has 2 atoms per unit cell. This means it will give rise to 6 branches. Now, in the last, I would like to tell you just briefly. This is just introduction, nothing more about more than that. So lattice, how these lattice vibrations are studied experimentally. How do we get these omega versus K diagram? These are studied or measured by inelastic X-ray or neutron scattering experiments. The inelastic scattering includes the emission or absorption of a phonon. And if you recall how we define phonon, it is a quantum of lattice vibration. Either it is absorbed or it is emitted. A neutron sees the crystal lattice chiefly by the interaction with the nuclei, because neutron does not have any charge, but it has magnetic moment, so therefore it will interact with the nuclei of the atoms. The kinematics of the scattering of a neutron beam by a crystal lattice are described by general wave vector selection rule. So this is the selection rule. If we have the incident neutron with wave vector k, and we have scattered neutron with wave vector k prime, so k and k prime are related with each other through this reciprocal lattice vector, and there is also a generation or absorption of phonon with wave vector capital K. So this phonon wave vector comes from the requirement of conservation of energy, and plus here denotes the emission of phonon, and minus here denotes the absorption of a phonon. For a phonon, we choose reciprocal lattice vector such that the phonon wave vector will lie in the first Brillouin zone. Now we try to understand it, how it is happening. The kinetic energy of the incident neutron is p square by 2 mn. Mn is the mass of neutron and p is its momentum given by h cross k, where k is the wave vector of the incident neutron. Thus, h cross square k square by 2 mn is the kinetic energy of the incident neutron. If k prime is the wave vector of the scattered neutron, the energy of the scattered neutron will be h cross square k prime square by 2 mn, and the conservation of energy requires that h cross square k square by 2 mn is equal to h cross square k prime square divided by 2 mn plus minus h cross omega. This is the energy associated with a phonon, and plus minus represents, as I told you, the emission or absorption of a phonon. Plus here represents the creation of a phonon, and minus here represents the absorption of a phonon in this process. To determine the dispersion relation using these equations 1 and 2, it is necessary in the experiment to find the gain or loss of the scattered neutrons as a function of the scattering direction k minus k prime. So, and what experiment is there? What is there in the experimental setup? There is a nice diagram in Kettle's book, so you can refer to the neutron spectrometer for this particular experiment for studying the dispersion relation of different crystals. So with this, I conclude here. This topic of lattice vibrations is complete from my side. If you have any question, you may please ask.